Colonizing space is the next great leap for humankind. Of all the inner planets in the solar system, Mars, the red planet, is most similar to Earth and considered the best option for human colonization. An abundance of materials and energy make it possible to construct a permanent habitat, a first step toward a human settlement, but you need a place to build. Scanning the surface of the planet, one location for our permanent station stood out: the Endurance Crater. Conditions on Mars are inhospitable and pose big challenges to human life. Because of the expense and limitations of space travel, we will need to maximize the use of indigenous materials and resources. The proposed strategy results from the study of the relations between three different but interdependent subsystems related to materials, printing system, and design. Our research is concerned with modeling the complex relationships between the associated variables. Our strategy builds on our current research to develop low-cost housing on Earth using parametric BIM design and additive manufacturing. The construction process involves a robotic arm printing a geopolymer concrete mixture called Marscrete. Marscrete consists of indigenous minerals, including basalt, which is crushed and used as aggregate. Kaolinite has to be calcined to obtain metakaolin, which is used as binder, and sodium and silicon compounds, which are used as agents to activate metakaolin with water, obtained from ice. We understand the hydration reaction with gravity by studying the solidification of concrete aboard the International Space Station. We are characterizing the material behavior by checking its printability and its shape deformation during the printing process. Results are then considered in the design of the toolpath. We are also studying the affordances of the printing process in terms of form and structure to determine the impact on design. An additional exploration path concerns the study of material effects to create aesthetically pleasing surfaces, both in the interior and exterior. Another key aspect stems from our research on the development of graded composite materials that permit a seamless and impermeable graded transition between opaque and transparent surfaces, such as our engineered geopolymer concrete and borate glass. The composite material is lightweight, thermally insulative, resistant to chemicals, freezing, and fire, as well as impermeable and protective from cosmic radiation. This technology promises to have significant impacts on building processes, architectural language, and the spatial experience of dwellers. Another key aspect is the development of functionally graded materials obtained by progressively replacing sand with lightweight aggregates, such as cork granules, which are used in the heat shield of spaceships. The selective use of functionally graded materials will enable us to optimize the performance of the habitat from the structural, optical, and thermal viewpoints. The glass gradient will increase towards the top to provide for ambient light. The cork gradient will increase towards the exterior surface of the walls to create a protective layer to shield the habitat from cosmic radiation and low temperatures. The design of the shelter is based on the constraints derived from our study of materials behavior and the printing system. These constraints were encoded into a parametric design model in Revit using Dynamo, allowing us to quickly explore different design configurations. They were also considered in the development of the toolpath generator and the construction simulator. Among multiple possible design options, we chose one to illustrate our concept. Each unit is composed of a protective shell made from indigenous geopolymer concrete and a lighter interior constructed from both indigenous geopolymer and recycled plastics, with 2 floors. By manipulating the seamless transition from geopolymer to glass, we can provide 2 types of openings: from above, giving each unit ambience lighting, and from sideways, allowing for views towards the Martian landscape. There are 4 units for work, living, sleeping, and gardening. Entry chambers on each end of the habitat enable access from the exterior and emergency exits. The first unit includes a wet lab, meeting area, and storage on the first floor, and individual workspaces on the second floor. These 2 different workspaces are articulated by a staircase. The second unit hosts the dining area, the kitchen, and bathrooms on the first floor, and a leisure area on the second floor, accessed by a second staircase. The third unit includes the sleeping quarters on the first floor and workout and leisure areas on the second floor. The design was conceived to enable visual communication between the various units and floors, thereby offering a spatially rich living environment. The fourth unit contains life support and hydroponic systems with provisions for emergency situations. Each unit can be sealed and will have life support capability during repairs. The hydroponic system in Unit 4 produces food and oxygen and treats wastewater. Floor ducts efficiently distribute all systems supplying clean pressurized air, water, and electricity. Gray water returns through the sanitary piping to be treated by the hydroponic and mechanical filtration systems. The wet wall distributes all clean and sanitary piping to the kitchen and bathroom fixtures. Piping for the wet lab branches out toward the work unit, which is also equipped with fume hoods for noxious fumes from chemical experiments. Solar film and nuclear thermoelectric generators create electricity, while two uninterrupted power supply units keep consistent power through periods of low energy production. The printing system is mounted on a rover. It includes silos where different processed materials are stored. For instance, concrete mixtures with sand, cork, or glass as aggregate. Each of these silos is connected through a conveyor to a dual mixer and pump. Each pump mixes the concrete with water and then extrudes it. By changing the relative speed of these pumps and using a dynamic printhead, it is possible to obtain concretes with different gradients. The dynamic head extrudes through a hose connected to a nozzle mounted on a robotic arm. A retractable dome guarantees a sealed and controlled environment with proper conditions for printing. Once at the desired location, the robot levels the ground and digs a trench. Then the dome is closed and printing begins. First the foundation footing, and then the ground slab. The exterior and the interior walls are printed at the same time. Penetrating frames are placed where required as walls are printed. Then it resumes to print the inclined walls, which become the roof, enclosing the habitat. Once one module is constructed, the rover moves to print the next module, and so on until the whole habitat is built. Then the habitat is sealed by enclosing the ports and placing connectors between units. These connectors have the mechanisms that will seal each unit in the event of an emergency. Stairs, rails, and furniture are then printed using small printers, and the installations are mounted. The habitat is then ready to inhabit. Motivated by additive manufacturing technologies and advances in material sciences, our research has become a platform to explore various interrelated topics that inform and transform design processes and the language of architecture. The conical spatial volumes inspire awe as our gaze scans their archaic and simple capacity, as the seamless transition from concrete to glass, united in a single monolithic structure, elevates understanding of their properties while providing an uplifting spatial experience.